Hi. In this video, we're going to discuss topics from Chapter 10 in Thornton and Marion, rotating reference frame and fictional forces. So, a great example of a rotational reference frame is Earth. Earth is a rotational reference frame. And when you have an accelerating frame like that, Newton's laws of motion are supposed to be with respect to inertial frames, non-accelerating frames. So how do we deal with that? Usually we don't really worry about that, but we might have to. So we're going to talk about finding the equations of motion, our acceleration, velocity, relative to the rotating reference frame. I have a picture of Newton on the slide here, because when I think about rotating reference frame, one of the first things that come to mind is a story about Newton corresponding with Robert Hooke. And I know you know that Newton hated Hooke, and this is one of the reasons why, is the story. He was trying to be nice to Hooke. He was corresponding back and forth a little bit with Hooke. And when he was feeling kind of good about, Hooke seemed to be giving him the deference he expected, he decided to give Hooke a little example of what he could do. And he was talking about if you have, the Earth and you have an object high above the Earth, if you drop it, of course it's not going to fall straight down. Newton talked about where it would land and the path it would take. And he made a mistake when he did this. And Hooke knew he made a mistake, spotted it, and of course, with great glee, corrected Newton. And you just don't correct Newton. That just ticked Newton off to no end, and he decided he would never correspond with Hooke again. And then you know more about the story of Hooke and Newton. So we're going to develop the velocity and acceleration with respect to the rotating reference frame, and that's what we're going to do in this video. Okay, so we're going to be talking about accelerating reference frames, in particular rotating reference frame, which is accelerating because it's rotating, and fictional forces that arise from those. Of course, so on my picture here, I have a boxcar or something that's rolling in that direction. It's accelerating in that direction. And if you have a pendulum that's hanging down and we're not moving at all or moving at a constant velocity, that pendulum would remain vertical with respect to a person in there because it obeys Newton's laws of motion. And you would have an inertial reference frame in that case. But if the frame is accelerating, if the boxcar is moving, then this would back, because you would have a net force from the tension in the cord that was accelerating that ball. So to keep it accelerating at the same acceleration as the boxcar. So if that were to happen, it would look like this. And to you sitting here, not knowing you're accelerating, it would look like something has moved the pendulum back, right? Or say you weren't sitting there and you were watching this from a camera and you couldn't tell that the boxcar is moving at all. So we call that a fictional force. It's a force that arises because you're in a non-inertial reference frame. It's not a Newtonian force. Okay. So let's talk specifically about a rotating reference frame. Okay. So let's say we have a reference frame, say on the surface of the Earth. So I'm just going to draw the coordinate system. Some kind of right-handed coordinate system. And I'm going to call the unit vectors that locate the directions E1, E2, and E3. So that's my rotating frame. And how is it rotating? So let me draw it down here again. E2, E3, E1. So it can be rotating arbitrarily around any of the axes. For example, let's say it could be rotating around the E1 axis, so the whole thing rotating at a rate I'll call omega 1. Or it could be going around, rotating around this axis. You're holding onto the axis, spinning the coordinate system around this way with a rate omega 2. Or say you're going around this with omega 3. So in general, you have all of this going on. So omega, in general, which is the rotation of our coordinate system, the rate of rotation of our coordinate system, is omega 1 E1 plus omega 2 E2 plus omega 3 E3. Okay, but Newton's laws of motion are with respect to a fixed frame. So let's write a fixed frame on here too. So this is a frame we're going to assume is fixed. And I'm going to call it a prime frame. So this would be E1 prime, E2 prime, E3 prime. So prime frame, that's our fixed frame. And the unprimed is our rotating frame. So we can locate the origins, the origin of the rotating frame with respect to the fixed frame by some vector, some displacement vector I'll call big R. So that locates the origin of the rotating frame with respect to the fixed frame. Now, we will have some object that we're looking at relative to both frames. So this is our object. I'm sorry, it's out of frame there. So with respect to our fixed or our rotating frame, we would locate that with some vector we'll just call R. But with respect to the fixed frame, so if I go there to there, we'll call that R prime. So R we'll write as x1 in the R1 direction, or in the E1 direction, plus x2 E2 plus x3 E3. So I'm just keeping the coordinate systems very general. I'm just using x1, x2, and x3. I'm not using x, y, and z or r, theta, phi. Okay. Now, we do recognize that r prime locates that with respect to the fixed frame ought to be equal to r, because you end up at the same object. Okay. We could also write that r prime is equal to, start here and go r plus little r. So what I want to do now is find the velocity with respect to the fixed frame of our object up there. But I'm going to write it in terms of our rotating frame. So this is going to be dr prime dt. So to simplify this, what I'm going to do is get rid of this. I'm going to say this is really the case. Our origins are located at the same location. So I'm going to get rid of, I'm saying big R is equal to 0. Okay. So that's the case we're going to have. R prime is equal to R. Okay. So I'm taking the derivative of r up here with respect to time. But now this is a rotating frame, so E1 doesn't always point in the same direction. Unit vector E2 is not always in the same direction. So when I take the derivative of this first term up here, for example, I have to take the derivative of x, leave E1 alone, plus take the derivative of E1 and leave x1 alone. So this becomes our total velocity. Do the same with x2. Okay, so obviously we need to find, for example, how E1 changes with time. So how can we do that? Well, look back up here at our picture of our rotating frame. So how is E1 going to change with time due to the rotation of these other two axes? If it just rotates about its own axis, it doesn't change its direction. But let's say when the coordinate system is rotating around E3, what's happening to the direction of E1? Well, it's going this direction. It starts moving in that direction as it rotates around the axis. So that's the direction of E2. So it's going to be, that's the rate it's going to change, the direction it's going to change. Because of the rotation around E3. But what about the rotation about E2? So as it starts to rotate, the coordinate system starts to rotate around E2 this way, E1 heads downwards, right? That's in the negative E3 direction. So it's going to be minus omega 2 E3. And that's it. It doesn't change direction because of the rotation about itself. And likewise, you can find how E2 is going to change with time by doing the same thing. It's going to change because of the rotation around E1. As that goes to rotation, as you rotate around E1, this vector starts moving up that way in the E3 direction. So you're going to have omega 1 E1. And then you're going to have, because of rotation around E3, you're going to get I'm not sure what I was doing here. When you rotate around E3, it goes into the page, it goes that way in the negative E1 direction. So I should have put a negative E1 there. Omega 3. I don't know what I was doing there. And then because of the rotation about E1, it's going to go up towards the E3 direction, so you're going to get plus omega 1 E3. That's what you should get for the change in E2 with respect to time. Sorry. And DE3 dt. I'll let you figure that out, and I'll write it down here. Okay, so that's how our unit vectors are changing in time we can use with this velocity. So one other thing to notice is that I can write this as omega, because we have omega written up here, as omega crossed into E1. And if you want to see that, here's E1 hat, E2 hat, E3 hat, omega 1, omega 2, omega 3. So omega crossed E1 equals, and then for E1 you put a 1 there. It's unit length. So there we go. When we do this cross product, we get omega 3E2 from this one. And we get 0 there, and we go the negative direction, 0. 0, and then we go down here, so we get minus omega 2 E3. That's what we get. So that's omega cross E1, and you'll get here omega cross E2 for this. Kind of neat, right? Omega cross E3. Okay, so there's our time derivatives of the unit vectors. Going back to our velocity here, I'm going to rewrite it with everything. Going back to this here, it was here. I'm going to write everything with E1 hat, E2 hat, E3 hat together, and then everything with E1 hat dot, E2 hat dot, E3 hat, the derivatives of those unit vectors. I'll write those together. So then I end up with x1 dot E1 plus x2 dot E2 plus x3 dot E3, and now the other one's plus x1 dE1. So I'm just writing these without the dots up there. I'm writing the derivative. So what I want you to know, so this is our velocity as seen from the fixed frame. What I want you to realize is this is the velocity you would see from the rotating frame, right? If you're in the rotating frame, you don't see the unit vectors changing. You're standing on the surface of the Earth. You don't really know you're rotating. So this is the velocity in the unprimed frame, the rotating frame. And then we have this over here. So how we can write that is, since V prime is this, plus, remember that is omega crossed into E1, but then I have this x1 here too, so I'm going to put that there. Plus, this is omega crossed into E2, but then I have multiplied by x2, so I could write that as this. And then for the last term, oh, not omega 2, that's x2. x3e3. And xe1 plus x2e2 plus x3e3, that's just r. So I can write this now. The velocity I would see from the fixed frame is the velocity you would see from the rotating frame plus omega crossed r. There we go. Fixed, rotating. Now at this point I should say that this is the derivative of the r prime vector with respect to time. This is the derivative of r with respect to time. And of course here's r. But since we had r prime, again, remind r prime was equal to r, this is the same as saying dr dt. Now I don't want to use prime, so I'm going to just remind you this is in the fixed frame because I'm replacing r prime with r here, equals dr dt as seen from the rotating frame plus omega cross r. So I have everything written in terms of r. Now, I have this in terms of r, but any vector that you have in the rotating frame, you can write this as, so I could write in general dq vector dt in the fixed frame is going to be dq dt from the rotating frame plus omega crossed r. For our example, instead of q could be omega. We could say d omega dt as seen from the fixed frame is equal to d omega dt seen in the rotating frame plus omega cross omega. But what is omega cross omega? That's 0. So the omega seen, the change in omega seen from the fixed frame is the same as in the rotating frame. So this is a picture of Professor Coriolis. He was a professor of mechanics. By the way, he introduced the terms work and kinetic energy in the form that we use them, in the modern form that we use them. But of course, he's better known for adding a term to the acceleration if you're in a rotating frame to get the proper result, and we call it the Coriolis force. So we're going to now talk about acceleration in the rotating frame and introduce the Coriolis force. Okay, so we have the velocity seen from the fixed frame as the velocity seen from the rotating frame plus omega cross r. I want to find the acceleration now, so I'm going to look at this. Okay, and remember we have this now too. Okay, so I'm going to, seen from the fixed frame, is going to be the derivative seen from the rotating frame plus, oh, I'm sorry, that's supposed to be a q there. I don't think I did that right on the previous page. Yeah, matter of fact, here's the previous page. That should have been a q. So then plus omega cross v prime. Okay. So the velocity, the acceleration is seen in the fixed frame is equal. Now I'm going to take this derivative with respect to time instead of v prime. I'm going to write that as v plus omega crossed r plus omega cross v prime, which is v plus omega cross r. Okay. So of course when I do omega cross v, let's go ahead and write this out, equals dv dt. So this is the acceleration as you saw in the rotating frame, plus, now I use the product rule here, so I'll have to write d omega dt as seen from the rotating frame, but we found out that's the same as the fixed frame, crossed r, plus omega cross dr dt is seen from the rotating frame. That's our velocity is seen from, our acceleration is seen from the rotating frame. Plus omega crossed v, that's this term right there, plus omega cross r. So boy, looks like we got a mess. Let's see what we can do with that. So this, the velocity seen from the fixed frame, we're going to call A prime, acceleration seen by the fixed frame, equals. This is the acceleration as seen from the rotating frame. Then we have plus omega dot, derivative of omega, crossed r. Now notice here we got plus omega cross. This is the velocity in the rotating frame, and that's that too. So we have two terms of that. So we have 2 times omega cross the velocity. There's supposed to be a velocity there. That's this. And then we have left omega crossed r. So this is from our fixed. This is from the rotating frame. I don't have a name for this, but this we call the Coriolis acceleration. So put a mass in front of that, it's the Coriolis force. And this is what we call a centrifugal acceleration. Again, these accelerations are not real. They don't arise from Newton's laws of motion. They arise because we're in a rotating frame. So they're fictional accelerations. So we get this funny motion. Again, just like you were in the boxcar, if the boxcar suddenly accelerated, it looks like the pendulum moved. Okay? There was not anything pushing the pendulum. It's because our reference frame accelerated. But there is an effect there, and we want to know. Okay, so let's try to do a problem here. So in this problem, we have a bug here, and he's on a wheel, and this wheel or disc is turning with a constant omega at a constant rate about an axis that goes here through the center, which I'll call the z-axis. The bug is crawling along a spoke in our wheel, and let's call that the x-axis, with a constant velocity. So the bug's going at a constant velocity along this direction, the x direction, and the wheel is spinning around at omega. What we want to do is find all the apparent accelerations that the bug feels. So, of course, in the bug's reference frame, he doesn't feel any acceleration because he's going at a constant velocity along the x-axis. So we're looking for these, the Coriolis acceleration, the centrifugal acceleration. There's no acceleration due to this because omega is constant. Okay. So, I'll write on this. Bug's moving along the x-axis, constant velocity v, so v is equal to v x hat. Omega is omega z hat. This was our y-axis. Okay, so we need to find the magnitude of this. It's the Coriolis. And we need the centrifugal. Now, if we're asking the apparent or fictional accelerations that the bug actually feels, let's go back to this. Acceleration seen from the rotating frame would be the acceleration as seen from the fixed frame. Then you would have minus omega dot cross r minus 2 omega cross v minus omega cross r. So these are fictional accelerations. We said this one's 0. It's not always 0, it's 0 for our case here. So we really need to find, as seen from the rotating frame. Okay, so what do we have? The Coriolis, we have 2 times omega cross v, so that's 2 x, y, z. Omega is in the z direction, and v is in the x direction. So you get omega v in the y direction. Should put the, and then that's it. Everything else is 0. So I forgot my negative sign. So the acceleration that we'll call the Coriolis is equal to negative omega v in the y hat direction. So he'll feel when you put a mass to it, you'll feel a force down in that direction, equal to how fast the rotation of the thing is times his velocity. The greater of those two, the greater the force. So yeah, if he has a mass m, then Coriolis force will be this times m. Now let's find the centrifugal. It'll be negative omega cross r. So omega cross, so we first do the omega cross r. So in this case, he's a distance x in the x hat direction. So I guess I should have wrote that r as he's x in the x hat direction. So omega cross r is omega is in the z direction, 0, 0, x. So that's just like what we did up above. We're going to get omega cross r is equal to x times omega in the y direction. So then we have, so that's equal to negative omega crossed x omega y hat. So then to do this cross product, and I forgot the mass here if I'm going to make this a force. So then I do this cross product. Omega is in the z direction again, 0, 0, and in the y direction we get x omega. So that's equal to, let's see, we'll get 0, 0, 0. We got to go in this direction. We get in the negative x hat direction, we get omega times x times omega. And that's it. So this ends up being negative, the mass, I put the mass in here, times negative x omega squared in the x hat direction. So I get mx omega squared in the x hat direction. So to summarize, here's our rotating disk, here's the x direction, here's the y. Here's our bug with mass m. He's going to feel fictional forces. One is in the negative y direction. That's the Coriolis. And that force would be mass times and then negative omega v y hat, and that's Coriolis. And F centrifugal would be m x omega squared in the x hat direction. So he has this other force in the positive x direction that he thinks. So this bug on this wheel feels like he's having a force that way and a force that way. Okay. So there we go. Now we're going to I'm going to write this, instead of accelerations, I'll write it as m a, the force from seen from the rotating frame, is equal to a force seen from the fixed frame. So obeying Newton's laws of motion here, this is what we would call a real force, gravity or whatever. Then we have minus omega dot crossed into r, the location vector with respect to the rotating frame, minus, I forgot, I need to be putting the m here, I'm talking about masses here, minus 2m omega cross v, this is the Coriolis, and then minus m omega crossed r, and this is the centrifugal force. So there we go. So again, the force you would see if you were on the rotating frame, you were the bug, be any real forces, so accelerations times mass with respect to the fixed frame, so that's any real force, then minus these different fictional forces. Okay, so this is what we're going to use to do some examples next time.